So this is essentially the definition of the topology file. Now let's look at server and the client. We are not going to cover this in detail, but essentially what I have here is simple Docker file that defines the hyperv image. So I am using as base image the Linux Alpine. In this image, I am installing bash and hyperv3, and I'm adding to this image my custom script server.sh, which it's really simple and starts the hyperv3 process as a daemon in port 6001, and it's going to log the information to the log file /var/log Kollaps server.log. So essentially, when I start the system, the hyperv3 process is going to be run. So this server script is going to be invoked. Let's look next at the perspective of the client. So the process is very similar. First, I'm going to look at the image. And the Docker image, as before, is really simple. I am using as base image Linux Alpine, and I am installing hyperv3 and bash, and my custom client.sh script, which is specified as follows. So the client script is a bit more complex. And why is that? Well, essentially, it's a bit more complex because if you recall, when I defined the topology, I defined 3 different servers. But let's go back to the topology to see this. I have defined the servers here in batch. So this means that all the 3 servers will be resolved by the server name. So this means that when a client starts, he needs to be able to somehow detect which server it needs to connect to. And this is what we do here. And we define that the first client should connect to the first server, the second client should connect to the second server, and so on and so forth. Of course, this would not be needed if I simply defined manually the servers. So another way to do this would be I would go to the topology and I would define here server 1, server 2, and server 3, and there I would say client 1 connects to server 1, client 2 connects to server 2, and client 3 connects to server 3. So this would be exactly the same thing. Here we do it in these 2 different ways to highlight that this is an option that you can also use. So I'm going to ignore these changes. So at this stage, I am ready to build my images. I've checked how they work. And let's see, how should I name the let's build first the client image, and my client image should be named Kollaps/hyperv3 client. So I'm going to build it manually. And as you know, I can build a Docker image by invoking docker build -t, which is the name I want to give, and I want to use this directory. Alternatively, and for simplicity, we also provide automated tools to build this. So if you check the documentation, we have this Kollaps app builder script that automatically builds the images for you, the ones that we provide in the examples, but for the completeness of the tutorial, we are building those images manually. So now the client is built. Now I need to do the same for the server. So I'm going to check the name of the image in the topology, and this is the right name to use. So I'm going to build the image with the tag name Kollaps/hyperv3 server as specified in the topology file for the current directory. And there we go. So at this point, I have defined or I have built the two different images. So I have the Kollaps base image and the deployment generator, which we saw before. And I have built the client image of hyperv and the server image of hyperv as well. So we still have one more step to go. If you recall correctly, in our topology description, we also defined the dashboard image, which we want to use for this particular example. So we have to also build it. So the Kollaps app builder does this automatically for us, but we are doing this manually. So let's go to this utils folder. And there we have the dashboard that we can also build ourselves. So let's check again the name of the image of the dashboard. It's Kollaps/dashboard. Again, the dashboard is not needed, but it's rather useful. So this is why we provide it as an utilities and not as the main part of the main distribution of Kollaps. So I'm again building the Kollaps image called dashboard on the current directory. After the image is built, you can check that everything is okay. So I have again the client image, the server image, and the dashboard image. So now I am ready to deploy this experiment. So now the next step is to build the topology in a format that either Docker Swarm or Kubernetes understands, such that it can be deployed. For this, we have the Kollaps deployment generator tool, which is provided with the distribution, and its usage is very simple. It essentially picks as input the topology file we just described, describing essentially this scenario with 3 clients, 3 servers, and 2 switches, and converts this topology to a file that can be parsed by either Kubernetes or Docker Swarm. In our particular example, we are using Docker Swarm, so we are going to use the -s flag. Otherwise, if we wanted to use Kubernetes, which is also supported, we should use the -k flag. So let's try this out. I want to invoke the Kollaps deployment generator, which is in the previous directory. For the topology file residing in the directory where I am now, hyperv3. The target system is Docker Swarm, so hence the -s flag, and I want to call this tutorial.yaml. And after this finishes, I have as a result a tutorial.yaml file, which for those of you who are familiar with the way that Docker Swarm works, this is essentially a Docker compose file. So you can analyze it if you want. You can tune it if you want for your target topology. In the usual use case, this is not needed, but if needed, you can tune this file to fit your requirements. We are not going to do this for this tutorial, so the next step is to run the experiment. At this point in time, running the experiment is really simple. I have a Docker compose file, so I just need to use Docker compose to make this run. At this point in time, running this experiment is really simple. So I have this tutorial.yaml file, which is a Docker compose file. So I just need to use Docker compose to run the experiment. To do this, going to follow the next step of documentation. So I'm going to deploy an experiment, and for this I'm going to use Docker stack deploy. So need to copy this Docker stack deploy. The name of the file is tutorial.yaml, and the name of the deployment is going to be tutorial. And this can be any name you wish. So as you can see, this creates the different parts of the system, the network, the clients, the dashboard. So now we can see that these different images are now running. So I have 3 servers, I have the Kollaps system, and I have 2 clients. And as you can see, this takes a while to bootstrap. But if I run this again, now I see that I have 3 clients, 3 servers, the Kollaps system, and the dashboard itself. So at this point in time, I have 2 options. One option is to use the dashboard directly to set up an experiment. The other option is to run the service in each one of the containers manually. So let's see this quickly on why this is useful. So let's say I want to connect to this particular Docker servers. Let's run this in another window. Okay, so this is easier. So I'm going to call this window server 1. The name of the ID of the container is this one. So one of the servers. So I'm going to run this. So let's check again the image, the container, sorry, identifiers. This is the identifier. So I'm going to run docker exec in an iterative environment of this image, and I want to run bash. So at this point in time, I am running inside one of the servers. And as I can see, there are no processes running here. So the container is running, but the application inside the container, which from our point of view is the iPerf server, it's not running. So now at this point, I have 2 options. Either I start everything manually, or I can use the dashboard. So let's try to use the dashboard. So first we need to find out where the dashboard is. So if we look again into the topology.xml, the dashboard is running on port 8088. So now I can use a web browser to just go to this port on this machine and access the dashboard. I can use a regular browser for the sake of our example, and to keep this only command line, which is rather useful. I'm going to use a command line browser, which is called W3M, and I'm going to access the local host port 8088. So this is the command line view of the dashboard. If you use a regular browser, the view is slightly more pleasant. So as you can see, all the clients and all the servers are ready. These are their IP addresses. I can go here to the active flows, and as expected, the experiment is not running, so there are no active flows. The graph part shows a graphical representation of the topology. Of course, this is not supported when running with the command line browser, but what I want to do now is just to start the experiment. As soon as the status of all the services is ready, I can start the experiment. So I can click here to start the experiment, and now you can see that all the clients and servers are running. If I go back to my server process here, and if I check for iPerf 3, I see that iPerf 3 server is running on port 6001, and it's logging to this log file. Now I'm going to exit this. I'm going to look into the dashboard again. Everything is running. I have some flows that are active. So there is a flow from client 2 to one of the servers with this throughput. There is another flow from client 1 to server 1 with this throughput. and there is a flow in the reverse direction, which is essentially metadata. And the experiment will run for the amount of time we specify it. And let's look again at our experiment. The clients start running at the beginnings. The servers also start running at time 0, and then after 2 minutes, all the clients will leave the system and the server will leave the system as well. So if we go back to our dashboard, we see that the containers are still running, but the active flows are no longer existent because the application stopped. So if I go back to my server process and I see that the server process of iPerf that was running before is now stopped, and I can go and inspect the logs that reside in this location. This is the regular log for the iPerf 3. And now with this log, you can use it for whatever purpose you deem necessary. And you can see that we have information such as the number of bytes, the bits per second, and so on and so forth. So the next step would be, I would collect these logs to my physical machine. I would do some processing, and this would conclude my experiment. Because the experiment is concluded, then I can go and stop the containers, and all the containers have now been stopped, and the dashboard also emits some important information. So essentially it's saying that there was no amount of metadata that was lost. This means that if there is no metadata lost, the accuracy of the experiment is very, very high. Okay, because if you recall, in our architecture, we have the emulation manager, which needs to communicate over the physical network with the emulation managers that reside on the other hosts. Of course, here, because we have a single machine, we have no packet loss, so the emulation accuracy is very, very good. And in the general case, what we have found is that usually in most scenarios, there is no metadata loss unless the cluster is under heavy load. So now I'm going to leave the dashboard. And as you can see, the images are still running because the dashboard does not kill these images because this is managed by Docker Swarm. So the final step, I need to remove this stack from Docker Swarm, and this concludes the experiment I have run. So with the dashboard, we can easily automate most of the experiments. But now let's say I want to do this manually for some reasons. So let's try this out. So the next step, I will start the experiment again. And now I'm going to call it tutorial number 2. Again, I am repeating exactly the same part of the experiment. So I'm going to check the status of the machines on the dashboard. So everything is ready. And recall that at this point, the containers are ready, but the application is not running. So I'm going to this server tab. I'm going to check the identifier of one of the server containers. So I'm going to connect to it as we did before in interactive mode, and I'm going to run bash. So the IP of this container is 10.10.19. So this is the IP I want my clients to use. And I am going to start the server process, but I'm going to do it manually. So I'm going to use the same command I used before. So iperf3 -j -s. I don't want this to be run as a daemon, so I'm going to skip the -d flag. And now the server is running. And to avoid the confusions, I'm going to name this window client 1. So I want to connect to the IP of the server we just started. The port is 6001, and I want to connect for, let's say, 10 seconds. So let's do this. And as we can see, the bit rate we have is around 10 megabits per second, sometimes a bit higher, sometimes a bit low. This is because of the throttling done by TCP itself, and this corresponds to the client that is running here. So to client 3 is connected to one of these clients, and the bandwidth that I have is around 10 megabits per second. Of course, this is the full bandwidth, so the application bandwidth will always be slower because of the network, the overhead of each of the different layers. Now I can try to do another experiment. So rather than use iPerf, I'm trying to ping this server. And as you can see, the ping is around 40 milliseconds.
As we specified in the target topology.
So now I'm going to go back to the dashboard. I'm going to stop the experiments. They were already stopped because they were not started by the dashboard itself, but it doesn't matter. So I'm going to quit the dashboard and to stop this experiment by invoking docker stack remove tutorial number 2. So this concludes the tutorial, and as you can see, this is really simple to do these kinds of experiments, even if we have arbitrarily complex topology. Here we are using a simple example, but of course the process is the same regardless of the complexity of the topology we are using. So this concludes our tutorial. There is much more material to cover, but unfortunately we don't have the time for it. I encourage you to check out Kollaps and Thunderstorm. Source code is available, and also check out the documentation that goes over these examples we have saw and many others in further detail. Thank you for your time, and now I am open to questions.